we're looking at compound sentences, and compound sentences in math. I mean, I'm a little iffy on the English and the grammar and the writing and the speaking, but the the math part of it just basically boils down to two complete thoughts that are merged with what we call a logical connective. Right? So those logical connectives, or at least the ones that we're going to focus on presently, are and or. Right? And so what we would do is we would look at the context of the situation to make a determination of whether the entire compound sentence is true based off of the individual components. Right? So it says right now I'm in math class. All right, yeah, that's a true sentence. I mean, depending on who the I is, but if we assume that it's the present reader, which is any one of us, then it would be a true sentence. This is math class. Right. And English class? Well, not necessarily. All right, I say not necessarily because I know that there is that situation where you have English class and then every now and then they open the wall and now it's like, hey, guess what? You're also in social studies class at the same time. It's like it is possible that you could be in one and the other at the same time, but typically not math and something else. They used to have a course here called Phys Calc, which was a combination of physics and calculus. So that would have been a science and math class at the same time, but it's not typical is really what I'm getting at. All right. So what we're looking at here is the connection of two different clauses of a sentence, true and false. The symbol for and, I call it an almost A. Some people call it an upside down V. I don't think that's as creative. All right, the almost A, almost capital A. It doesn't have a little crosshatch in it. All right, that honestly, that's how I remember it, because the or is the reverse of that. It's now that one really is a V, but I mean, there's nothing about the letter V that makes me think of the word or. All right, the symbol for and looks like kind of like an A, and starts with an A, so that's how I remember it. All right, so notation wise, we would say T and symbol F. Now we would be able to draw a conclusion from this, but common sense tells us that this whole sentence, I would think common sense would tell us that this sentence is going to be false, because there's no way for you to be in math class and English class at the same time. So we're able to draw a conclusion based off of our knowledge of the context and the truth of each individual component. All right. So then looking at number 2, right now I'm in math class, true. Or English class, I'm not in English class. So I'm looking at the two independent sentences individually and determining their truth. If I look at just the sentence, I am in math class, true sentence. I am in English class, not a true sentence, currently. All right, later in the day, maybe it's a true sentence. All right. This would read as true VF, or true or false. Now, if I read it as, the way somebody would ordinarily, most likely, read an or sentence in real life, probably throw the word either, or either, depending on how you pronounce it. Say I'm in either math or English class. Like if you're having a conversation with somebody, I can't remember my schedule. I know I'm in either math or English period 2. All right, and then you walk into math class. Oh, I was right. I mean, I think that makes sense. All right, you walk into English class. Oh, I was right. All right, you don't have to walk into both to be right. All right, you wouldn't be able to. All right, but if you walk into science class, you weren't right. I'm in either math or English class, and then you walk into gym class. I guess I wasn't in either math or English. All right, so if either part of this sentence is true, then the whole thing is going to be true, because just the context of it allows for that to be the case. Just thinking about how reality works allows you to draw that conclusion. All right, and I go back to the ordinary things, like I'm either wearing blue jeans or cargo shorts. All right, I'm wearing blue jeans. All right, it was one or the other. I satisfied my claim. If I come in wearing basketball shorts, then I was lying. You know, you're coordinating outfits with a friend. Yeah, tomorrow we're all gonna wear red shirts. You know what? I'm not sure. Maybe we'll wear blue shirts. We're either gonna wear red shirts or blue shirts. So some of your friends come in wearing red, some come in wearing blue, but then you come in wearing green. And they look at you and say, what the heck? You said red or blue. Well, what are you doing? You violated the rules that you yourself created, right? So that's really all there is to it, in terms of English sentences. But then we get into the math, all right? Because we can look at truth based not on perception but on the facts of the math. Like, for example, 3 plus 5 is equal to 8. That's a true sentence. 5 is less than 7 minus 1. 7 minus 1 is 6. 5 is less than that. That's a true sentence. All right? Both parts of these sentences are true. There's no reason to think anybody's lying. All right? So the whole thing should be true. All right? If both parts of a sentence are true, there's no reason to doubt that the whole thing is true. It's when one part of it is false that's when you start getting a little worried. All right? So if I tell you, and you just think about it as like the answers to a question on a test, or 2 questions on the test, and whether or not you pass the test, for example. Or your claim is I got all the questions right on the test, for example. You know, like I got a 100 on the test. In order for that to happen, you'd have to get every question right. If you're going to get a 100, most likely. So I would look at each part of the sentence and say, all right, well, question number 1 was 3 plus 5 equals 8. I got that one right. I said 3 plus 5 is equal to 8. All right, 7 minus 1 less than, 5 is less than 7 minus 1. I got that one right too. All right, on my 2-question test, I got them both right, so I got the whole test right. All right, that's all an and sentence is saying. All right. 10 plus 2 is not equal to 12. 10 plus 2 is equal to 12, so that's false. And symbol. 8 minus 3 is 5. 5 is greater than 0. That's true. This is where it gets a little weird, because it's not as simple as I'm in math class and I'm in English class. All right? What I would be saying is the first part of the sentence correct and the second part of the sentence correct? That's how I'm evaluating these mathematical sentences. Are both parts of the sentence correct? Well, no, the first part is not. So as an and sentence, I would have to say that this whole thing is false. All right, so as a rule, what we would say, if a sentence is separated by the word and, the logical connective and, the whole sentence is true if both parts are true. Otherwise, it's false. And we're only going to work with 2 parters, so 2 components to the compound sentence. So we'll say the whole sentence is true if both parts are true. Otherwise, it is false. The sentence is false. All right. But in the case of or, it actually turns out that if either part of the sentence is true, then the whole sentence is true. All right, if either part of the sentence is true, then the whole sentence is true. It happens. I don't know why. All right. The only way for an or sentence to be false is if both parts are false. All right. Bless you. So the whole sentence is true if both parts are true for an and sentence. Otherwise, the sentence is false. For an or, if either part of the sentence is true, if you got a T in there anywhere, then the whole sentence is true. So that just means that the only way for an or sentence specifically to be false is if both parts are false. All right. So looking at number 5, just going back to that, 3 is less than 5 plus 4. That's a true sentence. Or it actually doesn't matter what the second part of the sentence says, because the only way for an or sentence to be false is if both parts are false. So the second part is irrelevant. I don't really care about that, because the whole sentence is going to be true simply based off the fact that the first part is true. Because the second part could be true or false, and it wouldn't make a difference. We've already satisfied the truth requirement. All right? That would be equivalent to, going back to the math and English. If I said, I am in either math class or, and then you stopped, and you said, let me stop you right there. I'm in math class, so I don't even care about what you say after that. All right? It's true. It's a true sentence because I've satisfied the condition that I'm in math class. All right? Because it could be I'm in math class or, I'm on Mars. It doesn't make a difference. All right? We got the math class part. The second part doesn't matter. All right? 16 minus 20, that's negative 4. That's definitely not greater than 1, so that's false. And the 5.5 plus 4.5, that's equal to 10. That's not 11, so that's false. So that's the only instance in which an or sentence would be false. All right. So that's a little crash course on logic. We'll do more of that next week. But now we have to tie this into inequalities. All right. And this only scratches the surface on logic, because we have other types of connectors, like if-then connectors. The robots are a really good way of learning about logic, and we're going to spend some time with the Sphero robots. So that's the Unit 2 project coming your way. All right. Anyway, answer the following questions. Can you think of a number that is less than 3 and also greater than negative 1? All right. So a number that's less than 3, you just pick anything you want, but it also has to be greater than negative 1. Off the top of your head, I mean, you could look at a number line too. You can pull up Desmos if you want, but like 0 maybe? All right. Can you think of another one? A 1? 2? 1/2? Get some irrational numbers in there. Maybe you say like radical 2. Anything along those lines. These are all possibilities. All right. But in terms of a graph, a number that's less than 3, so x would be less than 3. And symbol, that number x would be also greater than negative 1. All right, so I need x to be less than 3 and greater than negative 1. So looking at the number line, I would plot each of these two inequalities separately. I'd say x is less than 3. All right, open circle on the 3, shade to the left. Greater than negative 1, Open circle on the -1, shade to the right. Oops. When we're talking about AND situations, we want what we call concurrence. We're looking for outcomes that happen for one value, or one, in this case, inequality, and also the other. It's got to be true for both. All right? So the whole sentence is true if both parts are true. So I need it to be true that the number is less than 3, and also I need it to be true that the number is greater than -1. The only numbers that satisfy that would be the numbers in between -1 and 3. All right? Because if you go down, you go by the numbers here. So we'll just take we'll take our compound inequality here. X less than 3 and x is greater than -1. And we'll look at, for example, so I'll test the value -2. Make a little table out of it. For -2, that number it's certainly less than 3. That's true. But it's not greater than -1, so that would be false. True and false is equal to false. So -2 would not be a valid number. So it wouldn't be part of my set. So I would have to disregard anything that's like -2. So maybe -3, -4, -5. All these numbers out here would be out of the mix. I'd have to disregard those. All right. We already tried 0 and 1, but we could verify them anyway. So 0, 1. 0 is less than 3, true. 0 is greater than -1, also true. 1 is less than 3, that's true. 1 is greater than -1, also true. So these two are valid numbers. 0 and 1 are valid. 2 would also be valid. Anything between -1 and 3 would be valid. But then you get beyond the 3, let's say in number 4. 4 is not less than 3, but 4 is greater than -1. That's fine, too little, too late. Both parts have to be true in order for the whole sentence to be true, so 4 is out of the mix. And so would anything beyond 4. All right, it'd fall in the same category. All right, so the only numbers that would work would be the numbers in between -1 and 3. So there's two ways to write that. One way would be to combine our inequality and say that we're going from -1 to 3, all right, because x would be living in between the -1 and 3. All right, it's bounded, it's trapped between -1 and 3. All right, that's the only way it could be true. The other possibility would be the interval notation, because if you remember, all we have to do is designate the start, the stop, and the fencing. All right, the start would be -1. The stop would be the 3. The fencing, and remember bracket versus parentheses. Bracket includes, parentheses exclude. Open circles, we exclude. So either of these forms would be true. Now you're on the hook for both forms. So when we take a test, you're going to need to know how to express these answers in these 3 different ways. We have this way up here, separated. We have this way here where we put it together. And then we have the interval notation. All 3 of these things mean the same thing, and you need to know all of them. That's why we're taking the time now to talk about it. All right. So the next one, it goes back to the can you think of a number that's less than -4, greater than 0. So this time it's an or though. A number that's less than -4, okay, like a -5. Or less than 0, well, I don't need it, I'm sorry, greater than 0. I don't need it to be greater than 0 because I already got it to be less than -4. All right. Greater than 0, like, well, 1 doesn't have to be less than -4 because it's an either or. All right. But I could write this as x is less than -4 or x is greater than 0. So this is one form of my answer. You'll find that the or situations are actually easier to graph because there's no overlap when it comes to or. So I would plot the -4 shade to the left to account for the x's less than -4, and then I would plot the 0 and shade to the right to account for the x's greater than 0. So there's only one other way to represent my solution here. All right, so I have this part. This is done. I can't write it as a between situation because x is not going to be in between the -4 and the 0. It's actually beyond. All right, but what I can do is write this expression here in interval notation. All right, so what I would say is, looking at my first interval or my first shaded region, that region starts at -infinity, stops at a -4. My second one starts at 0 and stops at +infinity. All right, so I'd say to myself, all right, where does this one start? Where does it stop? Where does this one start? And where does it stop? So the first one, like I said, starts at -infinity, ends at -4. Always got to think about the fencing. When it comes to interval notation, the fencing is the most important. All right? Because the start and stop should be easy to identify. Just pick it off the graph. All right? Infinity always gets parentheses. Open circles always get parentheses. In fact, the only thing that ever gets bracket would be a closed circle. All right? So 0 to infinity is my second piece. Infinity always gets parentheses. 0 has an open circle. So parentheses on the open circle. The only thing that, and this is another layer of notation that nobody's gonna like, but we got to do it. We have to unite the two sets to show that they're part of the same solution. So we tuck a little u in there. All right. So this is the first instance where we've had two separate intervals that make up the same answer. So that symbol means union. And that union is saying that when I write the -infinity to -4 and then follow that up with a 0 to infinity, I'm not saying that these are two separate answers to two separate questions. I'm saying they combine to give me one answer to this question. All right. So it's more math notation, but honestly, if you start thinking about this class, this whole course, as the course where you learn about the notation to set you up for success in the future, you wouldn't be wrong. You wouldn't be wrong about that. All right. Couple more. These will go a lot quicker. So consider the compound inequality. And again, folks, I mentioned this earlier. I know the temptation is to do the IXL and to tune out with the lesson, but you got to be thinking about your level of success coming down the line. If you neglect learning about this information at the expense of the IXL, what's going to happen is, well, you'll do well on the IXL, I guess, that 5-point IXL. But then when it comes time to take the 30 to 50 point unit test, you won't be ready for that. And then there will be the panicking. I'm not ready. Can I have extra time to study? Then you'll take the test. You won't do so well. Then you get your grade back, and then the emails come. I was looking through Schoology. I noticed I didn't do so well on the test. Is there anything I could do to improve my grade? Any bonus opportunities? You know, and it happens. You know, it's a common email, but it all comes down to moments like this where you have a choice between doing something other than what we're doing in class. There's only two problems left, folks. I'm just asking you to just bear with me for a couple more minutes. All right? I absolutely don't like teaching for an entire period. It's not often that I end up doing that, but it's got to be done in this instance. All right. So for number 3, I put the graph in there for you because it's pretty straightforward. It's going from -2 to 4. All right. That inequality, again, another way to write the inequality, you could do it a couple of different ways. For a compound inequality where it's in that trio form where x is in the middle, that's an and situation. I don't know why I wrote the word and like that, but I did, and I'm living with it. We could also write it as x is greater than or equal to -2 and x is less than 4. Or we could put it in the nice, concise interval notation, the start and the stop. Where does it start? Where does it stop? It starts at -2. Solid point at -2, so put a bracket there. It stops at the 4 with an open circle, so you put the parentheses there. You start looking at this, and hopefully it's questions like number 3 that make you think that there are some circumstances where interval notation is a little bit nicer to use.
How do you know if the -2 is a closed circle or?
Oh, because of the equal sign.
I didn't see that.
Yeah. It's a good question, though. Good question. All right. For number 4, the last one here, x is greater than or equal to 5. So I'm going to plot a closed circle at the 5. I'm going to shade to the right. It's also greater than a 0. This one's a little trickier because any number that satisfies either of these conditions is going to be true. All right. So sometimes it's worth it to just make the chart and say, all right, is it going to be true or false? All right. So another way to write this inequality, we start thinking about the truth value of it. So I'd look at it and say, all right, is the number 1 greater than or equal to 5? Well, no. And so why did I pick the number 1? Well, it's right here. It's in one of the shaded intervals. So I'd say x is greater than or equal to 5, or x is greater than 0. So I'd look at the number 1. The number 1, it's not greater than or equal to 5, so that's false, but it is greater than 0. So that's true. With an or sentence, all you need is one part to be true. So the 1 checks out. So 1 is part of my solution. Then you might try the 2, the 3, the 4, the 5. You try a bunch of values, but I'll try just 2 more. So how about the number 3 and the number 6? I just pick one that's in each interval here. And just see how it all plays out. So if I put the number 3 in there, 3 is not bigger than or equal to 5, so that's false. But it is bigger than 0. False or true, result is true. So that one checks out. 6 is bigger than or equal to 5, and it's also bigger than 0. So that one checks out. So it actually shows that everything, I mean, you could try more values to make sure, but everything bigger than 0 is going to satisfy this compound inequality. All right? So another way to write this would be to say x is greater than 0, because any number bigger than 0 is going to get the job done. All right? Now, this interval does go out to infinity, starting at 0, ending at infinity. So another way to write this in interval notation would be to say, all right, I'm going from 0 to infinity. Open circle on the 0, so parentheses. Infinity always gets parentheses, and that would be the end of it. All right. So that last one I think is probably the trickiest one conceptually, because you're looking at it and you're saying, okay, somehow if you look at it too haphazardly, you'd look at this and say, well, how did this become this? How did we just cancel the x is greater than or equal to 5? We didn't just cancel it. We looked at the different truth values based on everything that we talked about on the previous page. This is actually the culmination of the last 2 pages of notes. All right. So at this point,